Hi everyone. Today we're gonna start the topic about the controls, and of course for this class we focus on the classical control and uh one of the two major categories of the classical control is open loop control and the closed loop or the feedback control. So, and we have talked about the pros and the cons of both methods. For the open loop control, it's simple, it's straightforward. You use a controller to send an input signal into your system and then generate the corresponding output, and expecting this system output will match or being close to the desired system output. But the problem is all the model we used to describe the physical system is imperfect. Some model are better, some model are worse, but all of them are imperfect. None of them is the realistic. None of them are close enough to the real world. And the second is the initial and the current state is always imperfect. And we picked the state we're interested about in our system, but those states are usually comes with different noises in sensing and and sensing and the tracking. Also, the noises are everywhere from from the external environment and also from your own system dynamics as well. And inverting those models are pretty hard. Um, on the other side, the closed loop, the feedback control. In this loop, we introduced a feedback from the system output back to the controller, which is used to inform the controller for generating the corresponding system input. And this system input is supposed to kind of digest and kind of receive the information about the current system output, and better to help it generate the generate the corresponding input. Um, but the issue is in this way, since we introduced a new system, kind of introduced a new input when into the system, um, so this will change the system stability completely. So in this work, all right, in today's lecture, we're gonna focus on um, the feedback, the closed loop control. And the closed loop control is one of the most essential concepts in the classical control. It's probably not one of the most important, is the most important concept in classical control. Um, so this is a typical block diagram for the closed loop feedback control. And besides, we directly use a transfer function h1 of s to feed to realize the forward pass of the system from the input to the output. At the same time, we're gonna have another transfer function, another system response h2 of s, which is gonna go through, which is gonna take this current system output and convert it into some form, which feed back to the system input, and then generates the current error signal. And this error signal is actually the real signal that will be sent into the regional system, and then we keep this in a loop. So couple of terminology here. The first, the regional system response H1 of S, we call it a plant. This is typical. This is a plant, the regional system that generates the forward pass, generate the forward model. And the second is the in the feedback loop, in the feedback pass, we introduced a new transfer function h2 of s, and it is actually taking the current system output and then convert it, doing some mapping and convert it into some form and feed back into the current system input. So essentially, the H2 of S is taking the current system output. So uh, in real world, how do you measure the current system output is realized by a sensor? So for the simplicity, we just call the system or the transfer function uh, in the feedback path as a sensor. And two passes here. The first is the path going through the regional system, which is the forward path, H1 of S. And the second is the feedback path, which is taking the current system output and then convert it into some form which can be fed back to the system input and it generates the error signal, which is the real signal that used as input for the plant for the regional systems. So the transfer function for the current feedback system becomes this form. The H of S is still the ratio of the system output Y of S to the system input X of S. But because we introduced a new feedback path, the H2FS into such a system, so now the overall transfer function becomes H1 of S over 1 plus H1 of S times the H2 of S. And because the H1 of S times H2 of S will be used so many times, so we just add another notation here, T of S. T of S equals to H1 of S times H2 of S. And we call the T of S as the loop transfer function. Simply the term that we used to define this expression. And next is the error signal. Error signal is the signal that we actually fit into the regional system, plant H1 of S. The way we generate the error signal is that we use the input signal minus subtract the signal that's going from the signal comes from the feedback path. As we said, for the feedback path, we take the current system output as the input, right? The Y of S is the input for the feedback path, and going through the current introduced transfer function H2 of S, being converted into the form which is H2 of S times Y of S. That's the form you get after the system output going through the sensor, going through the H2 of S, right? And this signal is going to be subtracted from the regional system input X of S. And after subtraction, what we got is the error signal, the E of S. The E of S is the actual signal we're gonna feed into the regional system, which is called plant. So of course the system output, obviously it's just E of S times the H1 of S. So we have talked about all the elements in a feedback system or in a closed loop system in the simplest form. We have a few elements here. Plant, which is the system response of the regional signal of the regional system. H2 of S, which is the sensor used to convert the current system output into some form, and the subtract and the to combine it with the regional system input X of S. And the one thing you will notice in this feedback system is usually when we get when we take the system output Y of S and feed it into the sensor, which is H2 of S, and got the form after it going through the sensor. This is going to be subtracted from the regional system input X of S. So this negative feedback, since we are always subtract the y of s times h2 of s from the original system input x of s. So this is essentially a negative feedback. So the reason we do the negative feedback instead of positive feedback, this is decided by the empirical experiment, or is decided by the common practice to that we figured out that a negative feedback could be very effective to stabilize the system. So that's just being this practice just got inherited from the regional observation. So as we said, remember when we talk about these two type of different classic control method, open loop versus a closed loop, or versus the feedback control. The problems on the right side on the closed loop or feedback control is the feedback will definitely introduce the instability of the system. So now let's take a look at what's the effects of this feedback on the system stability. We have talked about the stability in the last lecture, which is a very, very important concept, which might be the first thing you will look at when you're trying to analyze a system either in the time domain or in the frequency domain. So now, since we have introduced such a feedback path, such a feedback into your system, which can help you. Definitely, it will have lots of benefit. We'll talk about the benefits later, but first we're going to analyze what's the effect of this feedback on the system stability. So let's first take a example. Let's say the current sensor H2 of S. Remember the transfer function on the feedback path H2 of S is the sensor. Simply it takes the system output, takes the current system output Y of S, and doing some conversion, doing some mapping to map it into some specific form which can be used to integrate with the current system input. So the most straightforward way is we just take the feedback. We just use a we just use a linear proportional feedback to the system output. So which is simply a constant k, no matter what the current system output is. The feedback will just be k times of the current system output. It's simply as we noted here, the feedback is linearly proportional to the current system output. All right, so just to plug in the H2 of S into the definition of the transfer function in the feedback system, it will be something like this. H1 of S over 1 plus K times H1 of S. So now let's say it's we have now we have uh, now let's assume that the regional system has the transfer function 1 over S. So this system response, the regional system response plant, which is actually a unit step function, right? This is pretty straightforward. You can check the lookup table for the transfer function of 1 over S. The corresponding signal in the time domain is a unit step function, right? So by using the definition of the stability from the last lecture, the current transfer function of plant of H1 of S is 1 over S, and then it has a one pole, which is 0, right? So because it has a single pole with a 0 real component, so the current transfer function H1 of S is marginal stable. This is pretty straightforward, just using the definition of the system stability in the frequency domain. And then let's take a look at the transfer function for the feedback system. if we use a unit step function for the regional system response. Once we plug in the 1 over s into this h of s expression, we will find the final form of the h of s is actually 1 over s plus k. So the for the transfer function of the feedback system, h of s, the pole is negative k, right? Um, the pole is negative k. So the real component of this pole, the real component of negative k will be completely random and just to be decided by the k itself, right? If k has a if as we can say, if the k have a positive has a positive real component, and then the system will be just to be stable, right? If k is actually a negative, is a if k has a negative real component, and then the system will just be unstable. And if k is 0 and has no repeated poles with the with zero real component, and then it will be marginal stable, right? So after adding, so in this case, the regional system h1 of s, a unit step function, is marginal stable, but after we introduce a feedback h2 of s, which is simply a linear proportional feedback in this system, and then the stability of the system will completely decided by this coefficient, by this proportional coefficient k. If the k has a positive real component, and then the system will be stable, and if k has negative real components, unstable. If the k is has a if k is 0 and has no repeated poles with the 0 real component, and then it's going to be marginal stable. So the feedback could change the stability of the systems in the completely different ways. And now more example, still about the effects of the feedback on system stability. Now the original system h1 of s is 700 over the s plus 3 times s plus 5. So h1 of s, the original system, is still stable, right? Both two poles for h1 of s is -3 and a -5. Both of them are has negative real component on the open left panel of the coordinates, right? So h1 of s is for sure stable. h2 of s, 1 over s plus 4, it has one pole at the -4. So again, it's also stable. But after we use the h2 of s as a feedback for the whole system, um, the new transfer function h of s is going to be in this very um, very complex expression with the highest order of 3, right? So now we're going to have 3 poles for this feedback system. It and use some way to calculate to get the uh, to get you make the denominator equals to 0 and solve it, get the poles of the transfer function of h of s will be -12.9 and 0.46 plus some imaginary number. So as you can see, actually two poles, both of them have the positive real component, which is the point 0.46 here, right? So those two poles are actually lying at the open right side, open right panel in the coordinate. So for sure, h of s will be unstable because we can never have the poles which have a positive real component, or in other words, we cannot have poles on the open right side of the coordinate. So in this case is the both regional signal, both the regional system response H1 of S and the system feedback H2 of S. Both of them are stable in the regional form, but the if we put them all together into a feedback system, into a feedback expression, the outcome transfer function, the outcome feedback system will be unstable. And this is the example, opposite example. The regional system H1 of S is actually unstable, which is simple. The pole of the H1 of S is 1, as which on the open right panel of the coordinate. But after you add a feedback, once again, it's a linear proportional feedback. H2 of S equals to 2 directly. And then the outcome feedback system will actually be stable. As you can see, the transfer function of it is 1 over S plus 1. So it has the pole at -1, which is on the open left panel of the coordinates. So h of s is stable. This example is exactly the opposite way as the last one. The regional system is unstable. The regional forward system H1 of S is actually unstable. But after you add a linear proportional feedback into the system, it will drag the system back to stable. So since we have talked about one, two, two examples. One is about going from the going from a regionally stable system to unstable, and the one is from a regionally unstable system uh, and then becomes stable through the by introducing a feedback into the system. And combining those examples, we can just get a very preliminary conclusion that feedback can make unstable system stable, or in the opposite way, make the stable system unstable. So um, it's simply not it's simply not sufficient to just analyze the stability of the regional system or analyze the stability of the feedback system. You do have to get the completed form of the whole system, of the entire system, and then you can make the you can analyze its system stability. And the easy example is a public address system. Or you're watching, you're on the online meeting of Zoom. Sometimes if you forgot to mute your microphone, and at the same time the gain of the microphone is pretty big, you will just hear those very annoying high-pitched sounds uh, from the communication. So that is a very simple and a very common situation. When the amplifier gain is set too high, the system will just go unstable and keep oscillating for its bounded input. Because when we talk to the microphone, the input is always bounded usually between like -1 to +1. But just because the amplifier gain, the feedback gain is not set properly, so the system is the amplifying system is going unstable, and will just generate those annoying high-pitched sounds. And this is just a very quick a very quick introduction about the effects of feedback on the overall system stability. As you can see, it can make unstable stable, and then also can make a stable system unstable. So the effects of the feedback can be quite diverse in terms of the system stability. We have talked about the effects from the system feedback on the stability, and now we want to talk about a couple of good things about the feedback. And there are lots of good things, and lots of the benefits and from this feedback, H2 of S. And in the different systems, mechanical systems compared to electronic systems, this feedback may play with different roles, may play with different positive roles. So let's first start with the example without um, any scenario. We're not constraining it into dynamic or mechanical or electrical system. We just simply look at this block diagram without any context. We define the forward path of the system uh, with the system response only as k, which is a linear proportional, which is simply a linear proportional amplification, right? Um, and then the feedback will keep the feedback at as H2 of S. And then if you write down the overall system transfer function, H of S is in this form, will be k over 1 plus k times H2 of S. So if you set the k as a very large value, and then um, in the denominator, the k times H2 of S will be way much bigger than 1, right? Way much bigger than 1 for certain S, right? If k is extremely big, no matter the value of the H2 of S, at least for some S, maybe not for all of the S, but for some S, k times H2 of S will be very big, at least way much bigger than the constant 1, right? So in the denominator, if k is extremely large, and then for some S, you can just approximate the denominator as just a k times H2 of S. So the overall transfer function of the system will become H of S approximately equals to 1 over H2 of S, right? Okay, so far is a very simple way, um, just using the definition of the feedback system to derive the current overall system transfer function, right? Um, so on the left side, we have talked about, we assume that the rational system is just a linear amplification of the system input, and the coefficient amplification coefficient is just a k, but this k is very large. So using the property that the k is very large, we can simplify the overall system transfer function as 1 over H2 of S. So if we use the cascade property of the transfer function and we add a block, we add an element into the block diagram, right before that, just to linearly cascade another block H2 of S into the system, and then essentially this system, the overall impact, the overall effect, or you call it the net effect, will be just a 1, right? H2 of S for cascades, if those two are connected in sequence, and then you just do the multiplication, right? If you multiply the H2 of S times the H of S, and then because of the current H of S is essentially equals to 1 over H2 of S. So if you if you cascade another H2 of S into this feedback system, essentially it's not gonna it's the overall feedback the no sorry the overall transfer function is gonna approximately be 1, right? It's simply like doing kind of like doing nothing to your system input, but still it has a list of benefits out of it. It's not simply just doing nothing to your input signal. Instead, in that way, it can be very robust, this system, if you take the input X of S and trying to generate the corresponding output Y of S. If you design the feedback system in that way and um, uh, cascade the feedback block into the system, H2 of S, H2 of S being cascaded into the system, and then the overall system will be very robust to the uncertainty in the forward path gain, which is the K. So no matter K is, let's say it's 10,000 or it's either the 20,000, it's not going to affect the behavior of your overall system, right? Because essentially the the transfer function of the overall system will not be affected by by this k anymore, right? Will not be affected by this forward path gain anymore. So this system will be very robust when you are either when you are calculating this k or you are calibrating this k, or either you are reading some properties from the electronic components. The k will be in a range of k. The value of the k will be will shift from the actual value, right? But if you design the system in this way, those arrows either in measurement or those arrows from the simply just from the modeling will not affect the overall behavior of the system, will not affect the final system output. That's the first benefit. This system will be very robust to uncertainty in the forward path gain. Okay. Second, of course, it will reject the external disturbances because we're converting, essentially, this system will kind of make the system output closely follow any system input. Or as you can see, the system output can restore the any system input. You can either say it's kind of tracking the system input, or you can also say it's storing the system input. Either way, um, this process will not be affected by any external disturbance because essentially the system output will always be the or always follows the system input, no matter if there is any interference on the system on the system itself. It's either there is interference or there is a disturbance on K or disturbance on the feedback path on the H2 of S. Any disturbance on those intermediate elements will not affect the system output. The system output will always closely follows the system input. Or you can say the system output will always restore the system input. So this is very beneficial because think about this is a wireless communication system. If you are talking, your voice, human voice is the system input X of S, and through certain um, like radio transmission systems, which will be easily interfered by any EMI. EMI is the electromagnetic interference, which is everywhere. It's as long as you are on the physical world, there are EMI which will disturb your system transmission, especially for the like the human speech or human voice transmission. It will be very easily it's very will be easily affected by those EMI interference. So such a feedback system can keep the system output closely follows the system inputs, um, regardless what kind of external disturbance are. Mm, talked about two benefits from the feedback system using this simple example when the regional system response is just a linear amplification with coefficient k, but the k is very large. And then the overall system, the overall feedback system, along with a cascaded H2 of S, and then it can be robust to the uncertainty in K in the forward feedback gain, and also it can be very robust to the external disturbance on the intermediate blocks, on the intermediate elements of this system. Okay, and then we are going to talk about another example, still, it's under the category of talking about the beneficial effects of the feedback system, talk about advantages of using feedback systems. So here is on the top of this slide, it's inverting voltage amp. So essentially, inverting voltage amp is gonna amplify your input voltage, and at the same time, it's gonna shift the phase of your signal by 180 degrees. Okay, that's shifted the phase by 180 degree is correspond to the inverting here, and the voltage amplification is simply just to amplify the magnitude of a voltage. So that's what inverting voltage amp will do to your to any voltage of your circuit. So, and here you can describe such inverting voltage amp as a block diagram uh, in in the bottom of the slide. This conversion is typically not required by this class. You need the domain knowledge, as we said, when you try to describe a system or describe a phenomena in the real world. Usually, you need certain type of the domain knowledge to describe it. If that's a dynamic system, the most basic building blocks are like Newton's law, or like in fluid, there are Navier-Stokes equations. Those are the equations in physics that help you that help you to model or help you to describe these phenomena. Um, and again, here is how you model, how you describe an inverting voltage amp. Um, for the details of those converting from the real inverting voltage amp structure, or from the inverting voltage amp architecture to the corresponding block diagram, this is typically this is usually not required in the scope of this class. But as you can see, this inverting, as you can see on this slide, this inverting voltage amp can be typically modeled as a feedback system, right? I've labeled what's the H1 of S and what's the H2 of S in the bottom block diagram. This is a feedback system cascaded cascaded with something, right? Uh, this part is a typical feedback system and cascaded with some other elements in sequence, in a kind of a sequential row, right? Okay, and then we're gonna focus on this block diagram. This is just the block diagram we used to describe the inverting voltage amp, right? Using some domain knowledge in electric circuit design, which is out of the scope of this class. So for this class, we're going to directly focus on the block diagram. that has block diagram is one of the one of the most very important ways to describe the system, right? As we talked about, there are multiple ways to describe system: block diagram, differential equation, state space model. All of those are different representations to describe a system. So here we used a block diagram, and as you can see on the left side, that's the item we cascaded into the system, and on the right side, this is a typical feedback system with the rational system response H1 of S and the feedback response H2 of S. And uh, following the definition of the transfer function for a feedback system, which is on the right side of which is on the right side of the block diagram, right? Again, I just want to highlight it. This part is a feedback system, and you can, using the definition and the transfer function definition, to get the transfer function for this part, right? And because we cascaded another item in the system, so essentially this cascaded term is going to be placed here, and this part is the overall it's an overall system transfer function, which is the ratio of the output to the system input, VOS over the VIS, right? That's the overall system transfer function, but because we cascaded another term into it, so we're going to have the extra term in the denominator. And on the right side, this is simply just to follow the definition of transfer function. Following the definition of the transfer function for a feedback system. That's the right side of the equation. All right, let's continue. So once we get the transfer function of the system, um, which is this one, the left side of the equation, and because we, as we said, because we cascaded another term into the overall system, and so we have this cascaded term in the denominator of the transfer function. Okay, but overall we can get the, if we move this term on the right side, we can get um, the the form of the rational form of the transfer function, which is V of S over VIS. Sorry, it's the VOS versus VI over the VIS. That's the form of the transfer function, right? Just right here. You simply just move the cascaded term to the right side of the equation and cancel some terms. You will get this form. Once again, I want to label it VOS over VIS. That's the transfer function of the overall system, essentially following the definition of the transfer function, which is the system output versus the system input, VOS over VIS. Okay, so this term is essentially the the transfer function of the overall system. And let's take a look at it on the right side of the equation. The detailed expression of this transfer function. So AI, sorry, A naught. A naught is typically when you receive a operational amp or you receive a op amp. A naught is the low frequency gain of this op amp, which is typically pretty large. The low frequency, what's the range of the low frequency? That depends on the specific op amp you are using. Typically, this range the low frequency stands for something between 0 to up to hundreds of hertz, like 0 to 200 hertz, stuff like that. That is in this range. Uh, the the gain the gain is usually pretty large, and uh, and this gain is essentially the A naught here. So if A naught is pretty large, yeah, if A naught is very large, and then if you look at the numerator and the denominator, and then essentially this term, the second term in the denominator can be just essentially can be ignored, right? Because A naught is extremely large, so the effect from the second term just can be ignored. And also, these two terms can also be ignored because A naught is large. So essentially, it's going to be, and if you cancel out the A naught in both denominator and the numerator, essentially you will just left the f of s and the zi of s. It can simply using one assumption here. It's not like one assumption, it's like one fact here, which is A naught. The low frequency gain of the op amp is very large. Simply using such a fact or such a observation, you can simplify the transfer function from here to here, which essentially you just have two parameters in the final transfer function expression, which is ZF of s and Zi of s. And let's continue. So now using the oh, sorry. All right, good. Let's back to the lecture notes. So, using the observation that A naught, the low frequency gain of the op amp, is typically very large, we can simplify the original transfer function, which is in this form, and then using the fact that A naught, the low frequency gain of the op amp, is extremely large, we can simplify it into this form, which only has two terms left, which is the ZF of s and the Zi of s. And let's see how this goes. Now, again, it's continuing the last page. When the A naught is large, the transfer function can be simplified into this form, and then we can just get rid of the effects from A naught, right? And then the transfer function, another way the transfer function is invariant to the change of A0, as long as the A0, the A naught is very large, right? So here is just an example to prove that when the A naught is very large, it is legal, it is valid to apply such a simplification from here to here, right? Using the rational form here, you just plug in a set of typical values from the op amp. For example, A naught is 10 to the order of 7, which is pretty large. Compared to A naught is 10 to the order of 6. A naught is large, but the differences of the change of A naught is also large, right? It's going from it is 10 times smaller now, right? In this comparison. But as you can see, the impact on the final transfer function is actually pretty limited. It's only a small differences in the imaginary part of this transfer function. So the change in the transfer function, I think it's less than 0.01%, but the difference is on the A naught, which is the low frequency gain of the op amp. The difference is the change is actually huge, is actually 10 times difference in the A naught, right? But the change on the A naught does not really affect the system behavior, does not really change the transfer function of this system. This is what we want, right? Because when you're designing an op amp, the A naught is from the measurement. It's from some pre-hand measurement when you are, it's like when you design the op amp, you fabricate it, and there is a specific range of the A naught during the design, right? But after fabrication, the designed value may not be the true value. So the actual A naught might be completely shifted from the designed value. Um, but the point is, even the actual value of A naught has been shifted from the real value, it doesn't really change the behavior of the system. Doesn't really change because it doesn't really change the transfer function. So the system behavior is still going to be consistent. That's really nice, right? Because no one can make sure that in the fabrication, all the steps are perfect or all the calibrations are perfect. There are always uncertainty. There are always noises in this process. But the good thing is that even there you have uncertainty, you have shift in the A naught. It does not really affect the system behavior, and that's another benefit of introducing the feedback into your system. And very quickly, we have got the end of this lecture. And again, we have some spare time for this lecture. So for the rest, about 50 minutes, we are gonna have again a pop quiz. Um, uh, Again, don't hate me. It's it's not gonna be graded, and the point of quiz, as I said many times, use it as a practice exam or use it for your future exam preparation. Do it by yourself or in a group. Um, Try to understand the questions in in a comprehensive way, combining the content we covered in this lecture and even including both those numerical technique and also those understanding on the concept in control theory. Um, yes, I believe those pop-up quiz could help you can deepen your understanding on lots of concepts, and will be very helpful uh, for you to become more comfortable on the future exam. There are two questions in this quiz. One is about the first one is more about the system description using the differential equations, which is a simple mechanical system. Two objects connected with a linear spring, and there is an external force F applied on one object. The question is, how would you describe such a system? Um, and what's the input and what's the output? Um, yeah, we have similar examples in the last lecture. Refer to it, and then um, think about how would you use those tools to describe such a dynamic system, such a mechanical system. The second question about you're given a transfer function. We're gonna analyze it first. Before analyzing, we're gonna ask you to calculate some specific values in the time domain. Limit when the t is approaching the positive infinity. What's the system output will be in the time domain. And the second is when the t is approaching the zero from the positive infinity. It's approaching zero from the positive axis. What's the system output will be still in the time domain. I think this form should look very familiar to you. We have talked about some theorems in the previous lecture, probably 2 or 3 lectures before, but it's a very important and also straightforward theory you can directly plug in to calculate those 2 values in the time domain. And be careful that the system input for this system is a unit step function, which is a unit step input, which is I don't think I need to describe on that part. Second question is to sketch the pole zero plot for this transfer function. Simple, like very simple and straightforward. Lastly, analyze its system stability. All right, and I think that is all for today. Those 2 quizzes may take you some time. Probably not that quick. So um, work on yourself. If not, talk to your friends. Work in a group. And check back the last and the previous lectures. If you have questions, bring up to the class or office hour on next Tuesday. Good luck on that and have a good weekend. I will see you next week.